So let me get down to it. The outline of this presentation. The first thing is that we're going to talk about the measurement of structural performance. Then statics just being a special case of dynamics, what the performance measurements can be used for, the importance of feedback, the current US approach, and the development of design codes. Now, I'll go through these in turn. The first thing is how to measure structural performance. This is top left here. We have a picture of the Manhattan Bridge in New York City. We use what we call a structural cardiograph. This is for archiving data, and we use triaxial accelerometers. And these are just about the most sensitive available anywhere in the world. They're actually produced in the United Kingdom. Now, we need power, which we can get from solar, or if we are lucky, then we'll get it from a building or somewhere close by. And we need to send the data back to our headquarters. So we do that, and we can do that by satellite communication. So everything can be run by solar power, and we send the data back over satellites if necessary. Now, I promise you, this is the only set of equations that I'm going to test your patience with. The first one, top left, is, of course, Newton's second law. Force equals mass times acceleration. And that, if you solve it for a single degree of freedom, then what you have is that the time-varying force acting on the structure is equal to, and this is mass times acceleration, and then the opposing forces. The first one here is a dissipation term, which is damping. And the last one there is the stiffness of the structure. If you solve this for that single mode of vibration, then you find that the displacement is equal to the force divided by the stiffness of the structure, and then this frequency response function here, which also includes the damping ratio. Now, that means that we actually have low frequencies, which are ideal for the use of accelerometers. We have a big response here, which is the resonance of the transducer itself, in which we actually use that fact for measuring velocity. So it's at the resonance, the response goes through 180 degrees, and actually at the response, it's at 90 degrees, as you need for velocity. So what can we do with that? There's that equation again on the top right. And in practice, this sets the scene for everything that we do and everything that people do in universities, the way that they look at the way that structures behave. And that's because if we use this equation and instead of having a frequency equal to the resonance frequency or a variable here, we set the frequency to 0. Then what we find is that the response equals the force divided by the stiffness. Statics, in other words. That's what we teach in schools. But it's only part of the story. If we actually take the frequency equal to the resonance frequency, then what we find is we still have response equals force divided by stiffness, but now we have a dynamic magnification factor. And up at the top right, you see that this dynamic magnification factor is actually 1 upon 2 zeta, where zeta is the damping ratio, and the j square root of -1 shows that we've gone through a phase change as well. So in other words, we've got a single equation which we can use either for statics or dynamics. And that does mean that there's a link between statics and dynamics. The dynamic magnification factor is all important here. Now, you would think, given that it ought to be fairly easy. Just multiply by the, divide by the dynamic magnification factor, and you've got the relationship between statics and dynamics. The problem is that the damping ratio is a very complex factor and it's nonlinear. For years, that's separated earthquake engineers and wind engineers. But now that we're looking at response and we understand these nonlinearities a little bit better, then we can actually move between the disciplines. So this is what we're actually talking about. If we have an example of a tall building, then we have sway. And if we take a spectrum in which we have frequency and the displacement on a logarithmic scale, actually it's the acceleration that we're using here. So we have resonances, and these are resonances of the structure. And you can see in this particular sway, if we're measuring in one direction, we get a big response. In the orthogonal direction, we just get a remnant. But we get an orthogonal direction frequency there as well, and not as we're measuring against that direction. But we do have torsion as well, and this is torsion and this is sway in the orthogonal direction. So using a power spectrum density, we can actually tell what these resonances are, and there's a lot of extra information as well. Going back to that equation, it's also the equation for design, because it tells you that what the displacement is going to be for a particular force. And now we've got the dynamics in there as well. We have the natural frequency of resonance or sway of the structure, the damping ratio associated with that mode. We have the mass of the building as well. But we can alter these things around, and we can say that the risk associated with that structure is its measured response, its measured performance over its expected response. Now, the expected response is what was used for design. So, in other words, sometimes we have to go back to the codes of practice that were in force when the structure was built, and we will compare the measured performance with that. Now, we can convert that risk ratio is a fraction, and we can convert it to a return period or a risk per year. So normally speaking, well, in the United States, we start off with the 50-year return period, and that is a probability of occurrence on average 0.02 per year. We talk about the 50-year response, but we don't wait around for 50 years to see it. It happens, and it can happen quite often. It's merely a shorthand for the amount of risk that we've got. Now, back in the BRE research days in the 1970s, we used an induced vibration scheme. We had 4 synchronized vibrators, and we shook structures. It's the only large-scale set of tests conducted on full-scale structures anywhere in the world. A number of places have done individual tests. But now, does that equation work? Well, turn it the other way around. And with a vibrator system like this, you have the force, which is very well defined by the amount of masses that you put on these turntables. The frequency is measured very accurately to 3 decimal places, and that can be converted. Knowing the frequency, you can convert acceleration to the amplitude. So we've got a varying amplitude here. We've got a varying frequency. It does change with amplitude. And then when we measure damping, as we do from this, with all of the different excitation regimes, we measure the damping ratio that occurs at that amplitude. And you can see it changes quite drastically. But the lovely thing is that when you turn that equation around and you calculate the mass of the structure, despite all these non-linearities going on, you actually find that it gives you a fairly consistent value of the modal mass of the structure itself. So this is a definition that those non-linearities compensate for each other insofar as looking after the modal mass is concerned. But the education process finds it so much simpler to take statics, or quasi-statics, that is. And as we educate people to use this type of approach, then code committees follow on. And what we do with code committees, and as I said in the introduction, I've been involved with code committees on 4 different continents. Then what we do is we like to work out how much a structure will deviate from its ambient position under the action of a quasi-static force. Of course, any force cannot be completely static because you put it on and take it off again. So there's some sort of dynamic approach there. So what can we use structural performance measurement for? The very first thing is structural commissioning. Now, we spend a lot of time after a structure is handed over commissioning all sorts of things. We commission the HVAC system, the building facade, the electricity supply, but we do not commission the entire structure. We are left not knowing how it's actually turned out. I'm going to come back to that and talk about that in some detail. Secondly, we can identify anomalies in the response of the structure. Thirdly, we can calibrate mathematical models. Finite element models are currently fashionable, and I say that advisedly because those of you who are old enough to remember, there were different types of mathematical modeling available to us. Finite elements, though, allow you to take a physical representation of a structure and turn it into a mathematical matrix equation. The fourth one is really rather intriguing because you can protect yourself. You can avoid liability by knowing what's actually happening. Knowledge is power. Using this risk ratio, looking at degradation over time, that is, if you've got a baseline, preferably obtained when you commissioned the structure, then you can watch how it changes through time. The next one is low amplitudes of response give information about the structure. And we do not have to wait until there's something very large comes up in terms of response before we can find out what the structure is doing. And in fact, I'm going to come back to that because it's really important. Baseline measurement of performance can be used to check changes in the structure as time passes. Before and after measurements, before and after some sort of event, an earthquake, a storm, or a fire. They are simple and cheap, and they are a method of assessing the damage, the holistic behavior of the structure after an event. A baseline followed by a calibrated model, mathematical model that is, can allow you to explore lots of different scenarios, play the what-if games with the model. So first, structural commissioning is a verification step that is necessary to help ensure that the structure have the needed capacity to withstand wind and seismic events that they were designed to resist. It includes testing of the structure to measure its performance. And a big example is the Opal Tower in Sydney. There was a lot of complaints. 169 apartments in this prestige building had to be emptied because the residents had heard loud cracking and there was all sorts of damage to the structure. A royal commission was formed. I don't think they have done anything as yet, though, or reported yet. Anomalies in the response. This I'd like to go into a little bit more detail. This building here is just by the side of the Kosciuszko Bridge. Now, Kosciuszko was a general who fought with the Americans in their War of Independence. The tallest mountain in Australia is Mount Kosciuszko, but it's called that because the mountain looks rather similar to somewhere near where Kosciuszko lived in Poland after he'd gone back there when the Americans refused to pay him. So in this particular case, we created a seismic event. Now, if you look in a little bit more detail, there is the Kosciuszko Bridge, and there is our structure. Now, we had a previous deconstruction assessment before the event. What they were doing was blowing up this bridge so that a new one could be placed by the side of it. They reckoned that they were going to have 1.8 inches per second, and that normally the classic information is that 2 inches per second and you're going to be okay. Well, we looked at this and found that the structure itself had a very flexible roof, and that in fact, by the side of the bridge, the movement was transmitted over to the back face of the structure. So the bridge was demolished, and the first mode at 3.22 hertz of this structure was only 50% of what would be normal for a single-story structure of this form. So the roof also had a resonance at 3.5 hertz, which was very close to the first mode sway, and it also had very low damping. So we identified what was going to happen if they went ahead with the test as it was, and there would be amplification because of the roof movement. So the structure is fundamentally weak. That's the bridge after it was blown up. We convinced them to increase the size of the berm so that falling sections of the bridge didn't create such a large force. And we convinced them not to blow up individual sections one after the other. The engineer in charge reported a change in 7 of 15 crack gauges of between 0.5 and 0.25 millimeters, and he said there was no damage. We, on the other hand, looked in rather more detail. The frequency changed from 3.22 to 3.15 hertz immediately. Immediately, the bridge was felled. A 2% difference in frequency equates to a 4% difference in stiffness. And look, the shape of the spectral response changed before and after what happened. So this is before and that's after. As a spectral response gets wider, it means that there's more damping. Now we use a version of the random decrement signature, which is actually a way of getting nonlinear damping from a structure. There are one or two mathematical niceties that you need to include in your algorithm so that you can get rid of singularities, but it is possible to do, and we've used it a great deal, including calibrating against those induced vibration tests. So what this did was to show us that before and after now, damping had risen from 0.9% to 1.5%. In other words, damping is much more sensitive to damage than is the frequency. And we calculate the risk ratio and convert that to a return period for that event, which would take the structure outside the elastic range. Before the filling of the bridge, it was a return period of about 13 years. After, it was 2.3 years. So what this means is that the wind speed that would cause the structure to exit the elastic range had reduced from 78 miles an hour to 66 miles per hour. And the code of practice for this region of the United States says a structure should be designed for 115 miles per hour. Next, the calibration of mathematical models. This is a large arch dam, and you can see it's very easy using finite elements to produce a model that looks really impressive. The problem, though, is that if you compare measurements with what actually happens, and this for a very large dam shows 1.65 hertz, there's the measured frequency, and the mathematical model 2 hertz. So there's an 18% difference between the real response and the mathematical model. In the second upstream downstream mode, it's 35%. After we've gone into the calibration of the mathematical model, then we're able to get very, very close to what happens in practice. Now, that's only a 35% difference. Sometimes we find differences of a few 100% between the mathematical model and the measured response. Now, the reason that happens is that a person who is doing mathematical modeling decides what to include in that model, and they can decide not to. If you're doubtful about somebody who is mathematical modeling, ask them, did you include the doors in your model? And they'll say, no, of course not. And then you say, glass panels? No. Who decides? Do you decide? Or is there some sort of technique that you've got? And of course, it all comes down to skill. Some people are more skillful at this sort of thing than others. Now, I want to go to this structure, which is the Fulton Street Transit Center. The Corbin building is an old icon, and we assessed it, we monitored it. This is one or two views of that building. And to the northern side, you can see this great big brick wall and a pit by the side of it in which they created the new transit center, which goes down to the World Trade Center. Now, looking at that, they were worried about it. The stairwell in the structure was of extreme importance. The stonework of the building was of importance. The stonework on the side of the buildings had cracks, and the floors had been partially taken up. There were cracks on that northern wall, but we did have drawings available. So we built a finite element model, including putting into that model that stairway. So that's the mathematical model. And what we found was that we were able to calibrate. And top right there is a mode of vibration, which shows what happened. I did a lot with this model, and the only way that I could get the calibration was to say, the floors are just 2 inches thick. Well, I ran into a lot of flack because of that. Nobody builds with 2-inch thick floors, they said. 2 years later, though, I took this picture, and that was because they were doing redevelopment of that structure. And there was a style of building in New York City over 100 years ago in which they used an arch formation between girders and then put dirt over the top and a wooden floor on top of it. And there, having taken off the dirt and the wooden floor, you can see what's left is a 2-inch thick floor to the building. So that's why the model only worked with a 2-inch thick floor. As a matter of fact, if you take a good look at some of the older subway stations in New York City, you find this same style of construction in there as well. The RFK Bridge in New York City, this is another thing that you can find with structural commissioning and with performance measurement. The two spectra here actually show the damping ratio obtained from the random decrement with a gusty wind, and on the right, light wind. And you can see they both come down to about 0.5% of critical, but at low amplitude with a gusty wind, you can actually see the interaction of wind and the structure. In other words, we have aerodynamic damping, and you can measure it using the random decrement function. This is a picture of Christchurch in New Zealand. One of the things that you can do with performance measurements is to assess a building very, very quickly. Now, in that particular case, the people who evacuated the buildings, quite a lot of them had left handbags, suitcases, and car keys inside the building. Question, can I go back in? Can I get my belongings? Well, with a performance measurement, it is possible to get a very quick determination of not just is it safe to go back inside, but also can we get people using the structure again at an early stage. Also in New Zealand, we had a magnitude 7.8 earthquake in Kaikoura, second on the southern island, and 50 aftershocks, which gradually got closer and closer to Wellington, which is their capital, which is at the southern end of the North Island. We had done a presentation for them, and as they found that these aftershocks were getting closer to Wellington, they became interested in what we might do to help them. So we actually had a look at 10 different buildings in New Zealand, in Wellington. And let me say there are various other things as well. This is the Manhattan Bridge in New York City, and we used performance measurements of the cables, the support cables, because they're supposed to be at the same tension. Well, you can actually measure the tension indirectly by measuring the natural frequency of the cables. This is in Sydney, Australia, and it's a very old bridge. And the question here was, is it safe to run the train faster over it? So we measured frequency and damping. Frequency was quite high, and damping was quite high. And you can see here a number of mode shapes of the structure, and there's the mathematical model. And question, can we release the train speed restriction? And the Indian Pacific, which goes from the Pacific Ocean to the Indian Ocean, went across this very bridge. And the question was, would it be safe to run it at 70 kilometers per hour rather than 50? And the answer was, yes, we can. This is a condo building, 2nd Avenue in New York City, where there was the 2nd Avenue subway being built underneath this building. There were two things that happened here. First of all, as the entrance to the underground station was made underneath this building, there was a load transfer. By using our dynamics techniques, we were able to monitor the load transfer and make sure that everything was going on okay. The conventional equipment failed, whereas ours continued. It was also possible, we saw on this balcony here, that something strange was happening. So we looked in some detail and found actually that a facade panel had come unstuck and was flapping about. But by measuring up here, then we were able to see that something was going on and stop anything from falling off. This is actually basement spectra. In other words, accelerometers set on the floor and looking for a void underneath the basement. You can see 3 different bays here. One has a resonance frequency because the floor is vibrating above the void. In the other 2, then it receives support. So that is a very simple and easy way of finding if there's a washout void underneath the floor. So performance measurements, is there a concern? Well, yes, there actually is. Because if you put all the measurements of the risk ratio onto one graph, like this one, then what we have is the value of 1 of risk ratio means that the structure is performing as the code envisaged. It also says that the mean values for New Zealand, the induced vibration tests, and for Japan and all buildings worldwide is somewhere 10 to 15%. Japan is 20% above code. And that's because people are naturally cautious. But structures age. And then we find that there's a large number of structures under 0.5 risk ratio. Now, that's just not acceptable. The structure in that condition is a real concern, what we call an outlier. Limiting liability. Now, in this particular case, we were called in to have a look at the effect of piles being driven. And what you can see here, the red line is the response of the structure, and the blue line is what happens when the harmonics of the piling operation occur. Now, what you see is that it is possible to get a correlation between that forcing function and the response of the structure. So what we did in that particular case was just change the driving rate very slightly, and you will not correlate this forcing function with what goes on. As a matter of fact, we also operated very, very closely to the person who was the operator for the pile driving that was going on. There was a requirement that this is velocity in inches per second, and that it would not go up too high. Well, they got a little bit concerned when it went close to 1 inch per second. They'd set a limit that they didn't want. So we stopped, looked at what was happening, and then restarted with a lower force. In practice, these people were the only ones in that area of New York that did not have stop work orders. So in other words, our operation, working closely with the pile driving team, meant that we could avoid the problems of people complaining about the vibrations that were occurring. Now, this is a really big one about avoiding liability. This is the Cadet Chapel at West Point in upstate New York. What happens here is that they use West Point to add new buildings, and we were looking at this Cadet Chapel. We made measurements, 5 different measurements in the bell tower, on the nave, and at the 2 transepts. Now, this is actually a view of some of the measurement positions, and that's where the explosions were being created a little bit away from the chapel. And that's a time history with a fairly large response at a particular time, just after lunch, which is what they normally went for. We looked at the response just to very light winds, and we found the frequencies were very similar. We got those frequencies out from wind excitation and from the explosions, although, of course, the explosions only last for a short time. So you really need a longer time to identify them. Well, we identified those quite well. And that's a close-up of the acceleration response at the time of one of the explosions, 1.8 Gs peak to peak. This is the conventional way in the United States of looking at these things, looking at peak particle velocity. In other words, a velocity response. But the problem is, it's fairly easy. You can see the time histories show a very ragged response. To get the frequency correct under those circumstances is incredibly difficult. If you get it wrong, then you translate all these points on this graph off to one side. Sometimes they get a bit bigger, and it's the difference between being above and below. However, this graph was produced in the 1980s by the US Bureau of Mines, And what it said was, well, we've got a lot of different types of response. We think that if you draw a line in, and this is the line, then you will be safe. So approximately 1 inch per second and 2 inches per second at higher frequencies. Problem is, the equipment of the 1980s was very inferior to what we use now. Velocity, peak particle velocity, was used because you're operating at the resonance of a transducer. So you get a bigger signal. Well, that was great in the days when we didn't have very good equipment, very good electronics, but now we do. So you can go straight to accelerometers and manage without having to have this extra large multiplication factor. What this said, though, was, and this was testing done on wooden frame domestic housing with mining explosions some distance away. It also concluded that the maximum amplification of a structure would be 4 times. We measured on the Cadet Chapel magnification factors of approximately 10 and instantaneous values that went even higher than that. So in other words, between the transept and the nave, we would have increased stresses. We had a big connection and raised the alarm, said if you've got a 10 times multiplication and you're holding the vibration intensity below 2 inches per second, then you've got to actually account for that and reduce the vibration at the base of the structure to 1/10. Well, 10 upon 4, anyway, 2.5 times less. So they did. They did that. And they said, well, where do you think the effect would be? We told them it would happen between the transept and the nave at the back side of the building, where the transept excitation was much bigger. So they went and had a look and found new cracking in those areas. Under that circumstance, they came to us and said, thank you. If you had not warned us about what was going on, then we would have been out of a job. We would have brought down the roof of that chapel, in which most of the generals in the U.S. Army have been married. Next, small response amplitude gives us information about the structure, and that is, if it's small, then the structure will vibrate on castrate about this level. However, if it's big, you've got soil structure interaction operating as well. This, for a long time, has been the difference between wind engineering and earthquake engineering. But in practice, we don't need to do that. We can measure under these conditions with just a small amplitude, exclude soil structure interaction, and find out what's happening to the structure. Well, if we do this small amplitude stuff before and after an event, we've got a measure of the structure. Not only that, but we can measure for a long period. And now with our very, very sensitive accelerometers, we don't have to wait for the large events. We can have just a breath of wind, and we measure inside this so-called elastic range. I'm going to say a little bit more about that later on, but inside the elastic range. So that if we have gross changes to the structure, we can see. We don't have to extract what the structure is doing from the soil structure interaction. And this is what it amounts to, that in practice, we make these measurements at low amplitude before and after an event, and we can see the changes in the structure. And this allows us to look at what's happened to the structure with a large event. We don't have to monitor during the large event, just after. And this allows us to expedite reoccupancy of a structure. Next, baselines. A baseline can be produced when commissioning a structure or at the first opportunity you get to look at a structure. This is our Excel spreadsheet version of it, in which there's damping, there's frequency, there's phase. And by looking at this, we can modify the frequency and look at the mode shape of the structure, both in plan and elevation. So with that, that forms our baseline. And we do this for each of the modes of vibration. If we have a baseline and a calibrated model, finite element model, we can examine the possibilities. Ariel Dam is in upstate Rio de Janeiro and provides drinking water. We measured the response and got first mode of vibration at 1.65 hertz, and we were able to look at that finite element model and see what might happen to it. Well, what it says is that we have severe damage in some places and stress concentrations in other places. So, if we look at the structure, we can say, okay, we have damage in this region, and the finite element calibrated finite element model says that damage will occur in these two regions if it experiences large forces. So we've got three sluice gates. What do? We open the middle one first, we open this one second, and that one third, depending on the amount of water that's going over the structure. And that way you reduce the forces operating on the dam. Since they didn't have the money to repair the structure anyway, they loved it. The next section is system theory. And if we apply system theory to everything that we're doing, the whole process of codification, of building, and then using that building. Well, the first thing is structural design is intended to deal with forces. We specify the forces that occur on structures, and we do it pretty well, actually. But we don't know that new buildings meet their design intent, or if there are existing buildings that less capacity and pose a risk. Now, I was asked a question before we started about older buildings, and we have actually tested an 80-year-old building in New York City, one which fortunately had some very early measures of frequency. So we had effectively a commissioning of the structure done, and we were able to go back and take a look at it. And it had lost, over the 80 years, something between 10 and 20% of its capacity. Still okay, because it was built with a lot of spare capacity. But system theory, when it's applied to this whole process, what it says, it states unequivocally that any system without feedback is unconditionally unstable. So in other words, if we don't find out what our structures are doing, then something is going to go wrong sooner or later. So that's why we are saying, yep, we should actually be looking at the response of structures. The US has actually identified that this could be a problem. So they formed a committee. The US has an international building code, which only applies in the United States at the moment, but it has a very good document, ASC 716, in which lots of aspects of similarities to Eurocodes, to the best codes around the world are contained. In fact, people on code committees tend to share information anyway, so it's not surprising that similar advice appears. Now, the mission statement for forming this committee is this, or from it. It's not the whole mission statement. And I'd like just to read it to you because it's so important. It is the way that modern design codes are almost certain to have to go, because we must be looking at performance. Although nearly all modern design specifications are targeted to achieve some level of performance, most structural design today is not performance-based. Rather, typical design procedures evaluate design acceptability through conformance to prescriptive criteria on materials, configuration, detailing, strength, and stiffness. Such criteria are deemed to result in structures capable of achieving acceptable performance without clearly defining the performance expectations. Furthermore, the engineer using such prescriptive procedures does not explicitly verify the ability of the structure to achieve the desired performance. And that's where they're going. That's what they want to do to make sure that the system theory feedback loop is completed. I sit on that committee. I represent the Institution of Structural Engineers on it. And this is why. This is the sort of thing that's happened. First of all, the Tay Bridge disaster, 1879. Dreadful thing. It was a storm. The bridge collapsed as a train was going over, and a lot of people were killed. So after that, instead of £15 per square foot, instead of £10 per square foot, the requirement was increased up to 15. The Tacoma Narrows, that really showed us that dynamics was important. And again, we just went to £30 per square foot. And then we started introducing dynamic effects. Between 1950 and 2000, codes were prescriptive. 89, the National Institute of Science and Technology and the National Science Foundation actually identified that performance assessment goals were important. And then the report sat doing nothing for another 30 years. So right at the moment, we stand on the threshold. We are able now to move into the realm of performance-based codes. So what we're actually saying here is that the majority of design codification that has happened is involved with specifying forces. We do it on the basis of a return period, or rather a risk that we think is acceptable, and we work on that. But we haven't got dynamics into the codes. What we have is quasi-static forces. We work out a response, and then we put a dynamic magnification factor if the building or the structure meets certain criteria to make dynamic response important. Dynamic response became appreciated by the work of Alan Davenport at the time. He was at Bristol University, subsequently moved to Canada. He did a lot of work with wind engineering, very good work, absolutely revolutionized it. And what we had then was effectively mean and gusts, which were important. They still get confused. People talk about the two things interchangeably, and we use a 3-second gust at 10 meters for design these days. And the reason we do that is that we think we know the relationship between the gust and the mean wind speed. We don't. It changes under a whole series of different conditions, like the boundary layer, like zero plane displacements. These have their effect, and it can be quite complicated. I would far rather that we actually used the mean hourly wind speed that we used to in the United Kingdom a long time ago. But 3-second gust is the flavor of the day. So here we have assessment of capacity and risk, and I'm coming to a finish now. What we're saying is that capacity is governed by this equation, which relies on Newton's second law of motion. And all we have to look at is frequency and damping, because if we're measuring before and after an event, this equation here tells us about the linear elastic range. Well, I think I've shown you that there are so many non-linearities that there are actually no such things as linear elastic behavior. So many of these non-linearities are sort of compensating for each other. And if we put them together, though, frequency and damping, then what we find, and this diagram here is actually used in earthquake engineering now. The first part is for the wind engineering fraternity, and this is for the earthquake engineering groups. So if we have a damaged structure, then this changes. The modulus of elasticity of the entire structure changes. Risk? Yes, we can measure that. It's the measured performance over the expected response. And as a matter of fact, we have a patent on how to do this using these nonlinear parameters. So we can go to this this risk ratio and find out what the effective return period is. I would like to just point out this diagram produced by a good colleague, John Main, at the Building Research Establishment. Each one of those red dots represents a 50-year event. That is a 0.02 risk per year of occurring. And you can actually see that it doesn't happen as the clock strikes 50 years. Sometimes there are 4 in a 50-year period, sometimes 1, sometimes none. And in fact, the statistics are quite consistent with this diagram because it shows that 63 of these 50-year groups are empty. And that's what the statistics tell you. That is what we should expect. So these two parameters are important, frequency and damping. So fundamental frequency for buildings, produced by my colleague Brian Ellis, 46 upon H, now appears in the US Code of Practice as well. Bridges, Reto Cantini, who worked in the European theatre for a long time, produced this diagram. So in other words, just by looking at the length of span or the height of a building, you can have a very good estimate of what the frequency is going to be for these structures. What about damping? This diagram here is produced by Yukio Tamura in Japan. There is a 3-part curve as an estimate of what damping should be. There's no elastic zone. It's actually an approximation. So what you've got is a rise in the damping characteristic as the amplitude of response gets bigger. As the matrix of the material in the structure actually creates areas that rub. In other words, it's not viscous damping, it is friction damping. If you take enough friction elements, then what you have is something that approximates viscous damping. Randex signature from a mode you can see quite often, we have high damping at low amplitudes. So what's going on? Well, this structure in New York City, we had a garage just in front of this and a new HVAC unit going in there. When they took the garage away to do some work, they found this great big crack and they repaired it. We put 2 accelerometers on either side of the crack. So what you have here is a picture of the most expensive crack gauge anywhere in the world ever produced, because they're about $3,500 each. And this was what happened with the damping characteristic. Before, we had a rise in the low amplitude of damping, and after they'd patched up that crack, we had this 3-part curve. So in other words, just in one test, we verified this 3-part curve. And in fact, once again, Yukio Tamura's curve says we've got this 3-part curve, but we also look at what happens we get rises in the low amplitude plateau when there's interaction going on with the structure and its surroundings. We get this rise with damage. The curve rotates, and then the high amplitude plateau lowers if there's damage because of all the minor damage elements in the structure having just used up their energy. So for a bridge, there are mechanisms of damping, which are dissipation in the material, construction joints, energy dissipated into the foundations, interaction with the air, and energy dissipation by friction with adjacent structures. And that's actually the Iron Bridge in the UK. So this is a series of bridges in New York City, the RFK Bridge, and we did measurements on that, the suspension bridge, the lift bridge, and truss span. What we've done is over 200 structures. We have information from these and a database which occurs. So finally, why is it so valuable? Well, the first thing that we do is to say to people, use this technology and it will save money. It identifies weak buildings before the damage becomes so intense that you've got to do something in a panic. You can prioritize budgets because if you know your group of structures that you're responsible for and which are the weak ones, fix the weak ones first. And with that, you can spend your money more efficiently. You can assure that work meets the design intent. That's commissioning. So if we do that, then we can see that the structure has actually risen to or above the design intent. After events, quicker reoccupancy. In Christchurch, there was a building which survived the initial earthquake. It then had a series of smaller earthquakes, and with a smaller earthquake, it collapsed. And yet people were ready to say, yes, it's okay, it must be okay because it survived the earthquake. Well, in practice, if you go in looking at the performance of the structure, you see a gradual ratcheting down of its capacity. So these objective measurements help assure safety. And the point is that measurements allow the structures to be compared based on risk. And it's an appropriate use of system theory for structures. Liability as well. Knowledge is power, as I said. So this sort of thing gives you due diligence. If you're going to buy a structure and you want to know whether it's worth buying, then do a performance study. Compare with what the design originally said, and you can be absolutely sure of what you're spending on. So finally, there are various different types of structure that can be used with these techniques. In practice, there are all sorts of different types, and any structure that can be viewed as a system can be subjected to a performance assessment.
Fantastic. Well, there we go. Alan, I could probably speak to you all evening if I was if I was allowed to. But we've got a really good collection of questions, so we'll start running down those in a minute. But I guess my takeaway is that we're always learning something when we measure. And I suppose I was reflecting on the fact that we so very rarely get to measure the buildings that we build, and maybe that's one of your your key messages. I also was thinking that actually our ability to predict the performance of our structures is perhaps not always as good as we might think it is. I think I probably spent the first 25 years of my career thinking that I could predict anything if I put enough finite element power into it. I think I'll spend the next 25 years concluding that everything is more complex than I ever thought it was. I just wondered though, I wanted to come in with this question just to get us going. You've learned an awful lot by having that ability to both model and to measure structures. And I just wondered if you could share with us what do you think's been your biggest surprise in that process of modeling and measuring?
Oh, I think I get a surprise every time I go to a new structure. It's never quite as we expected. And you are right that there's a lot more still to be learned. We're much closer to looking at, excuse me, at what things ought to be like. But there are little nuances. And one of the things that has been the biggest surprise to me is what's the effect of adjacent structures attached in some small way to the structure that you're particularly interested in. And people will often say to us, well, there's an expansion joint there. So, of course, they're separated. Well, they never are, actually. They always transfer some sort of energy between them. And I find it difficult to get over to people that may be the theory of what you want to happen, but the practice is not quite the same. The other aspect, I mean, I've spent more or less most of my first research career and then experimentation and projects here looking at damping and the way that it changes. So the mechanisms for damping are they're difficult at times, but we've got a really good handle on it now. And the thing that surprised me right at the beginning, I was brought up thinking, yep, viscous damping. And then reading carefully, it was equivalent viscous damping. And then Tom Wyatt came along with something which was a new mechanism in which, without saying it, he'd actually used fracture mechanics. And that was the key. So once you put all that together, then what you find is that sum it to infinity, and lo and behold, you actually have equivalent viscous damping with a friction mechanism. So now you've got the mechanism and you've got the equivalent viscous to work with because it's so much simpler to work with. And that was a surprise.
That's fantastic. Yes, I can completely connect with that detail of the movement joints. I think one of my favourite jobs ever, which has to remain anonymous, but is known amongst the people who work with me as the building that goes bang in the night, was all about all about movement joints and locking up. I rarely come across a movement joint that's that actually does what it's expected to in practice. Alan, I was going to move to some of the questions though from
Sure.
our audience, and I'm going to kick off with a question from Anna Maria, and she thanks you for a very interesting lecture. She would like to understand, when you talk about the calibration of a model, what does that actually entail, and which parts are you trying to modify and match with the measurements you're taking in the field?
Well, the match is done through the dynamics, or at least that's the first thing to do. The more modes of vibration that you tie up between what you've measured and what the finite element model says, then the more complete the model actually becomes. So in other words, get the first mode, that's relatively simple. Get the second mode, where the structure is effectively doing a a rumba type dance with stomach moving around. And then the third and the fourth mode, the more that you can get, the more accurate does your finite element model become. So in practice, what I do, I normally start with that simple case of the sway of a big building, or the vertical motion of a bridge. Then get that one right, and then you find that the interaction with the abutments become more important, or a building with its plinth become more important. So then you have to make adjustments down there. You'll also find at that stage that you're saying, oh, well, wait a minute, it's not a straight line equivalent. It's actually got variations here. So we might want to adjust the stiffness, perhaps even the E value at different floor levels to tie up with the structure. And then there's a theory that says if there are a certain number of imperfections in a structure, the number of modes that you need to define them is just one more than those imperfections.
Excellent. Well, picking up on that question of imperfections, Hare Krishnan answers and asking, following a high intensity event, there could be cracks which develop in the lateral stability systems, and he's postulating that they might actually remain closed during the ambient vibrations that you spoke about, and he's asking, these might show influence on the stiffness only under significant loads. So how do you go about thinking about that, Alan?
That's a really good question. First thing is, a crack will work and dissipate energy only when the two sides are actually rubbing together. So if it's open, the amount of damping is actually going to go down. And then what you have is there are three parts to fracture mechanics there. So elongation of the crack also creates energy loss. But now this I have experience with, because in Hong Kong, we took concrete core samples out of a tall building from the top, the middle, and the bottom. Same pours of concrete in various different places. It had been subjected to a typhoon, very high forces. And so we did a scanning electron microscope study on those samples, and we found a chemical difference in the sample from the top of the structure. Now, in practice, this Wyatt model for damping, which relies on fracture mechanics, says at the low amplitudes of response, there are really big interactions, like with floors and walls, the building and its next adjacent structure. And then you get cracks occurring, and they work. And gradually, as the amplitude goes higher, you get smaller and smaller cracks. And there are equations in fracture mechanics for how much force you need to elongate a crack. But of course, the final stage is everything is used up, but we've actually put an extra element to that, in that there are chemical changes right at the very biggest amplitudes of response as well. Fascinating stuff. I'm told that we have similar sort of mechanisms that occur in steel as well, but I haven't done experimentation on that.
We've also got a number of questions about cost. So a number of people, Alan, asking about the cost of doing the measurements on a structure's performance, and actually, justifying that to their clients. Can you give some idea of the sort of costs that you think about when you're talking to clients?
Well, it depends on the size and complexity of the structure, of course. If it's a domestic house and we can get it done in a day, then the costs are as little as $2,000 or $3,000. If we're talking about a 3 or 4 story structure, then probably working its way towards $20,000 US dollars. This is. It depends on the amount of effort that goes into it. So, I mean, those prices really, if you're going to look at the cost of building something, and then should I actually do a commissioning, which is going to cost me $10, $20, $30,000, it's a no-brainer, really. You really ought to be doing it.
Thanks, Alan. That's great. Now we've got a number of questions here about some of the values which are actually used during modelling. So I'm going to combine a couple of questions here, so you can come back to us. Jorge, who I would say appears to be listening from Madrid, so just expanding your international audience there. He's got a great question about your opinion on the typical 5% inherent damping value adopted in the seismic analysis of concrete buildings. And Sanjay's been asking about how you chose some of the specific values you used for shear modulus when you were doing the work on the Ariel Dam. How do you think about those values that you're putting into the analysis that you use? What are your tips and tricks?
First of all, damping in earthquake codes, typically people use 5%. Yeah, I think that that came about because of a throwaway phrase that I put into a paper a very long time ago, and that was looking at a time stepping response and noting that anything over 5% gave the same sort of response no matter what you did. You could increase it to 10, 20%, and you got the same. So 5%. Yeah, but there is a real problem there, and I suspect that that was going on in Wellington, and that is that at low amplitude, if the the damping value is small, as it is, then what happens is that the structure will rise to a bigger response amplitude faster than you expect. The people in Wellington said, "Look, we looked at the code, we got the earthquake amplification right, and yet our buildings got damage. Why? Well, because they spent longer at an amplitude which was higher than they were expecting." So there we go. That was really a justification of that. A paper that I wrote a very long time ago looked at what happened when you put in nonlinear damping and a regular 5% or something like that. And I found that under certain circumstances, you could get 100% difference in the response. And of course, bigger because of nonlinear damping. It's not taken into account at all in design at the moment. So next thing, shear modulus and things like that. That's a very good question. Where do you start? The interesting thing is that we work with stiffness elements. So in other words, what we can do is adjust them. You've got control over stiffness, which in some suites of programs, you find that they'll just tell you choose a member, and we'll tell you what the E value is and shear modulus and all the other things that are there. But in practice, the thing that really makes the difference is the joints. How are the different parts of the structure connected together? How do they transfer load? And you've got all sorts of things. When you look at the detail inside the response of that's measured of a structure, then it's very clear where you've got to introduce these areas of a structure where loads are being passed more easily or more difficultly.
Excellent, thank you, Aaron. Well, iStructure have told me we can take just a couple more questions, so I'm going to carry on just for the moment. There's a great question here from Aaron. I'd love to hear your answer on this. So your approach with accelerometers, how does it take account of structural fatigue when you're measuring the performance? How do you deal with those fatigue issues?
Well, if a structure does have fatigue in a certain part of it, then what you'll find is that the holistic stiffness of the structure will change. So that, in other words, the displacement per unit force, and this is modal displacement and modal force, that ratio will change. In effect, there is a Young's modulus for the entire structure, a holistic value, which represents the displacement per unit force, and that changes. So the other thing that you have to take into account is ductility, because some can be used up if there's a big event. How much? Well, you're not sure, but if you've got a change in the holistic stiffness of the entire structure, then that gives you a point to work from. And quite honestly, as in the stress strain curve, now we're taking stress strain and moving it to the holistic, the entire structure. So instead of stress strain, we've got force displacement. So under these circumstances, there's an area where there's elastic going up a certain way and then bending over until you get to the yield point. To a reasonable approximation, it's a flat line from there. So if you've got a change, then you can work an estimate of how much ductility you've actually used up.
Thanks, Alan. I'm going to finish with a question from John, which I think sort of reaches to the heart of where many structural engineers here in the UK and across the world are at the moment, thinking in terms of the demands of climate change and circular economy. And John asks that with the need to reuse rather than replace buildings, how can the techniques that you've spoken about this evening potentially be an enabler and driver for that approach? Have you got any thoughts on that? Is that an area that you work in, Alan?
I don't work in it, but it's an excellent question because, of course, if you are going to extend the life of a structure, it's really important that you understand what's happening to it. Has it lost capacity? Is it an increased risk? Well, by simple measurements and leaving a simple sentinel accelerometer, because we are, after all, looking at the entire behavior of the structure. If you've done a baseline, you know measurement at any point will give you information about other points. That one point will also give you the natural frequency. If that changes, the stiffness has changed. And you can use the random decrement, the amplitude related random decrement, to look at changes in damping. Changes in damping are a really good indicator of damage occurring. They actually tell you about fracture occurring, because if you've got fracture, then it depends on a certain length of element. And that means that at a particular amplitude of response, you get a sudden excursion in the damping characteristic. That's a really good indicator that you've got a little problem there.